So hi, everybody. It's really nice to be here and thank you for the opportunity to give a talk. I'd like to apologize in advance because there are some constructions near my house, unfortunately, so you may hear some background noise. So hopefully it won't interfere a lot, but in any case, it matches because I'm going to talk about how do we study the dust in the X-rays using background sources. So let's see how this will go. So first of all, let's set the stage. In the interstellar medium, we have this, if we really zoom in, we can see all those tiny particles that are called the dust grains. So the dust grains are very small in size, about 1 nanometer to 1 micron, and they're characterized mainly by their chemical composition and morphology. So by chemical composition, I mean, what is the chemistry of interstellar dust grains? And we know today that it's composed in vast majority by carbon or silicates. Silicates is this group of minerals here that you can see, magnesium, silicon, oxygen, iron, that are also the refractory interstellar elements. And they are gathered in two famous groups, mainly in two famous groups, the olivines, with this chemical formula. Please note here the 4 atoms of oxygen in comparison with the pyroxenes, that they have 3 atoms of oxygen. And also I said that the dust grains are also characterized by their morphology. And with that, what I mean is whether they have the atoms into the grains are in order. So we have the crystalline grain compositions, or they are disordered. So we have the amorphous grain composition. So now, dust grains are really important for many physical chemical processes in our galaxy, also causing the polarization, as it was mentioned before. However, there are still open questions regarding the properties of interstellar dust. So here we are focusing mainly on the oxygen and iron content of interstellar dust. And what we try to understand is, where are those elements? These elements are missing from the gas phase, and we still cannot find them exactly back into, for example, in another form, for example, in dust. We cannot find all of it. And this is the so-called, for example, oxygen budget problem, as you can see here, illustrated in this plot. So in higher densities in the galaxy, the combined contribution of silicates, oxides, ices, and CO gas cannot account for all the missing oxygen. And also, we don't know exactly what is the iron inclusion into dust yet. And can X-rays give us an answer to these questions? Well, yes. In the galaxy, we have a lot of low-mass X-ray binaries that we use them as a flashlight. They light our way through the interstellar medium that contains both gas and dust. And what we observe with the X-ray satellite is an absorption spectrum that brings both the information of gas and dust. Yes, so we use them basically just as a flashlight, those X-ray binaries. So, but what is the process? So in the case of a single atom, here illustrated here, the absorption of a photon corresponds to a certain edge in the spectrum. Instead, when we have the dust, we have multiple atoms, basically we have together atoms. So the outwarding photoelectron will interact with the neighboring atoms, and our wave function will be modified due to constructive and destructive interferences. And around the photoabsorption edge, we will get this pattern here, as you can see, which are called the X-ray absorption fine structures. And these are the fingerprints of dust, basically, that we study from the X-rays. And these features, basically the shape of these features reveals what is the chemistry of interstellar dust. So this is an illustration, an unrealistic case, basically just an illustration of the X-ray energy band. So we can see here that we can study the photoabsorption edge of elements going from carbon to iron. So here you can see, for example, that we can study the oxygen and iron edges using the XMM Newton satellite, and we can study with Chandra the magnesium and silicon edges. In the future, we will be able to study the iron K edge, the dust in the iron K edge, using the Athena, or if you prefer, Athena telescope, and we will be able to probe very dense environments of the ISM. And also, we might be able to study carbon, the carbonaceous matter of dust grains, using the mission that will be proposed that is called ARCUS. So this is here just a simple illustration of a spectrum in the silicon K edge. So this observational data, Chandra data, and you can see here basically that only a gas model cannot reproduce our data. And we have these features here that are the X-ray absorption fine structures that we need to model to understand the chemistry of interstellar dust in the different lines of sight that we study in the galaxy. So in the literature, there were some models of dust. However, what we needed is a concrete model, a self-consistent model that account for all the photoabsorption edges and for many different chemical compositions of dust. So we can study the chemistry of interstellar dust with much more freedom. And for this reason, we went to the laboratory. We acquired, this was a long project of, I think, 6 years. We acquired models of dust using either the synchrotron facilities in France, where some collaborators in the group acquired measurements for the silicon and magnesium bands, and I went during my PhD in South Spain, in Cadiz, at a microscope to acquire measurements in the iron and oxygen. So our dust samples are about 20, and they contain silicates with different ratio of oxygen and also different magnesium to iron ratio, basically to study also this question whether or not we have magnesium-rich silicates or not in the galaxy. We had also oxides and iron sulfates. You can see here some examples. So basically, we had some silicates like olivine, also some oxides like magnetite. This is also famous for its ferromagnetic properties, and some iron sulfates. And also, we are planning next month to go back to the laboratory to study also metallic iron. Some of these samples are natural, taken from meteorites, and most of them are basically synthesized at the laboratories in Vienna. And most of them come also in both crystalline and amorphous form, so we can also study the crystallinity of interstellar dust. So this is the first part. Basically, we go to the laboratory. This is an image of the electron microscope. As you can see here, this is a dust sample. Basically, we put the dust grains, as you can see, this black powder. Basically, we put on a small on a thin layer that is located here, and then we have an electron beam that interacts with this dust sample, and what we measure is the kinetic energy of the electrons after the interaction with the change in the kinetic energy of electrons after the interaction with the dust sample. And you can see here, basically this is a raw laboratory spectrum in the oxygen KN and iron edges here, as you can see. So once we acquire all the laboratory measurements for these 20 samples, we want to translate this spectrum to something that our X-ray fitting packages understand, because the final goal is to fit the X-ray absorption spectra and understand what is the chemistry of interstellar dust in the lines of sight we study. And we come to part 2, which is the computational part. So here what we use basically we calculate the dust extinction cross-section, and what we used is the mi-scattering code. Here we use the Python version, mi-Python. And because also the dust grains come in different sizes, you don't expect to have only one size of dust grains. We have to integrate over a dust size distribution. And for the first approximation here, we have used MRN with this range, basically. And we are now working on including also larger grains. Here you can see a picture from the laboratory of the dust. Basically, this is a region onto the sample, not exactly the dust grain, and where the color bar is a thickness ratio. And what we calculate in the end is the dust extinction cross-section, which has both, of course, the scattering and absorption components here. So we do this calculation for both the oxygen and iron features for all the 20 samples, we have our different models, and what we need to do is to apply them to the X-ray spectrum. So we use a sample of sources along the galactic plane. These sources have been selected according to their column densities. Basically, depending on which edge one wants to fit, you have to select a different sources at different column densities. Here, we work in the oxygen and iron K edges, which are located in the soft X-ray band below 1 keV. So we need to have column densities approximately 1 to 5, 10 to the 21 EV/s. If we want to study the silicon and magnesium, as has been done before, we choose all higher column densities. So we study all those sources, and we basically, for the X-ray spectrum of all of them, we feed all the different dust combinations that we can have. So we have more than 1,000 fits combinations, and we select what fits better in our spectrum, and we can understand the chemistry of interstellar dust. This is one example for one source, is this source, this column density. And here you can see the Chandra HelAS spectrum and the XMM Newton spectrum here. So basically what we do is that we combine the capabilities of both X-ray satellites that carry high resolution X-ray instruments, so that we can have the maximum spectral resolution in the X-rays for the edges of our interest. So we use Chandra for the iron and XMM Newton for the oxygen. And here you can see in green is in transmission of dust. And as you can see, most of the iron L edge is described by the dust, while little contribution comes from dust. And this is somehow expected because iron is mainly depleted, is mainly into the form of dust, into the interstellar medium. And the question was oxygen, because it has been debated whether or not you can study the dust from the oxygen K edge and how much of the oxygen is depleted into dust, and if all of it or some of it that we find from the X-rays can be characterized by the dust models. So here you can see, zoom into the oxygen edge, and you can see that, for example, we can probe, except of the dust, also the different phases of the ISSM by studying the ionic column densities of the oxygen species. We can see from oxygen 1 features to oxygen 7. And you can see here again the transmission. So basically this is the dust, as you can see here. So there is some contribution from dust that basically helps the absorption. And you can also see the gas here. So we do the same exercise for every source. As I said before, we feed all the different spectra, and we come to some results. So in the lines of sight that we're looking into, which are diffuse sight lines, we find, I heard that, thank you. We find magnesium-rich pyroxene as the main dust chemistry, and also some amorphous olivine with this formula, as you can see here. We find an upper limit on crystalline dust, about 20%, and most of the iron, more than 90%, is locked in dust. And we have about 10 to 25% of oxygen in dust, depending on the line of sight. So less depleted than the iron, of course. And we find solar abundance of oxygen with respect to our reference value that we have here. So in this last minute, I'd like to speak a little bit about the future of X-rays, because the current instruments enable us to study the interstellar medium and dust, but in the future, we'll be able to do much more. So soon we will have the launch of CRISM. CRISM is the recovery mission of Hitomi. It will be launched about 2023, as far as I know. And you can see here is a simulation with CRISM in the silicon K edge with only gas. And you can see what basically we can distinguish. So except of studying the dust, the different dust species, as you can see here, we will be also able to study in great detail the dust size, basically, because there is this peak here that is a scattering peak, the scattering component of extinction, that CRISM will be sensitive to that. And that will be really, really great, actually. And also in the late future, we will have Athena again, which is with this telescope, we will be able to study the iron K edge, which we cannot study with current instruments. And this is great because with the iron KH, we can probe very dense environments of the interstellar medium. So we can even make comparisons by studying the iron edges in diffuse interstellar environments and the iron KH with dense environments. So that will be really great. And finally, there is the concept of ARCUS. It will proposed to be launched together with Athena, and ARCUS will give us great spectral resolution in the oxygen KH. As you can see here, we will be able to see a forest of absorption lines in the oxygen, and also disentangle much better between the gas and dust phase in oxygen. And I will leave you with my conclusions, and thank you very much. And sorry again for the background noise.
Thank you, Ioana. Are there any questions for Ioana? Yes, Grigoris, go ahead.
Hello. Hi, Ioana. Nice talk. I would like to ask you, these observations are along the line of sight, right? So yeah. In that case, is it possible to constrain the distance where you find this dust? For example, how close to the binaries could these structures survive or be?
Yeah, that's actually a great question. Yeah, we've been wondering about that for quite a while. The thing is that, so one thing is that indeed what we study is all the dust in the line of sight towards the source. So for the moment, we cannot say that, okay, this dust comes from this layer, from this distance, this dust comes from this layer. Unfortunately, for the moment, we can't do this. However, we can, for example, if some lines, but not the dust, but some lines gas lines that come from some hot gas, for example, oxygen 8 lines come from around the binary. There have been some tries now to disentangle and say that this comes from around the binary. Basically, very, very hot transitions might come from there. But yeah, we're actually working on this right now. So yeah.
Okay, thank you. And there is another question by Gina.
Hi, Ioana. This is very exciting. I'm just curious, how do you make the powders?
That's a great question. So some of them are natural. So they're taken from meteorites and make them in powders. So another, so the ones that are synthesized are basically made by quenching of a melt. I don't recall all the details because they are made in laboratory in Vienna and they come to us in the laboratory, but I can send you the reference on that and talk about it. Well, I think it's the similar procedure when you make glass, basically, but I don't have all the details in the top of my mind right now.
Cool, thanks.
And the last question by Kostas Koulibatzakis.
Hi, Ioana. Very nice work. Thank you very much. I would like to ask, could this be possibly applied also to extragalactic sources?
Great question. Actually, we tried to apply to the LMC. The problem is that, so to do this, we really need to have high spectral resolution to be able to distinguish the dust features because they're really small features and our spectra are very noisy. So what we have experienced so far, also by trying to study AGNs, the dust in AGN, is that we don't have yet enough sensitivity, but that could be done possibly with future instruments even better. But indeed, I can direct you through the work of Rogantini, I think 2019, where they tried to do for one extragalactic source as well.
Thank you.